Hello, students. Today we would like to continue utilizing the theory of the derivative to analyze functions. So what I'd like to do is present a couple of functions that utilize the prerequisite material with the new structure of the derivative to give a more precise analysis of the function. So let me share my screen. The first function is of interest to us because it will combine some of the trigonometric functions that we spend much time with an algebraic function. So when we have functions like this, we simply have to have some of the calculus structure to be able to analyze in ways that were not available to us in the prerequisite courses. So let's exhaust both possibilities. Now, what we see here is we have a restricted domain, but what we want to notice is that this function is defined for all real numbers, and there are certain qualities of this function that you may find interesting. So here's an aside that I want to mention first. That is, if you notice here, we can extend this to all real numbers. So on the real line, f of x is odd because what you see, sine is an odd function, and of course, x is an odd function, so that makes 5x, and of course, negative 10 sine x odd functions. And the sum of two odd functions is also odd, so this gives us f of x is odd. So if you determine any detail in this particular interval, you can transfer that detail to the interval negative 2 pi to 0 just by transferring all of that information through the origin, because we know that the odd function has symmetry relative to the origin. So this gives us free material. So again, some structure may require that a domain be restricted because of the fact that we cannot extend it. That is, it's not defined. For instance, like square root functions and things of that nature. So when we have the ability to extend to all reals and make certain observations, we should keep that in mind. Now, one thing I want to notice is that we have EVT here. So EVT gives us a max and a min on the closed bounded set, just for observation. So we have a continuous function, closed bounded set. Now, what I want to do, ladies and gentlemen, is just simply evaluate the function at the endpoints just for additional information. So f of 0 will be a negative 10 times the sine of 0 plus 5 times 0, which again, 0 of sine, or sine, what is it? All integer multiples of pi are zeros of sine. Of course, 0 is an integer multiple of pi, 0 times that, right? So we get 0 plus 0, which is 0. Now, before I move on, I'm noticing something that might be good. Let's go ahead and factor this, make it easier to evaluate. So we can say negative 10 sine x. And then, of course, 5 divided by negative 10, that'll just be a 1/2. So we have minus x over 2. So note, this might make the evaluation a little bit simpler. If we run the negative 10 back, we get this. And of course, the negatives absorb, and 2 into 10 is 5. So we get exactly what we started with. So now, of course, let's go ahead and look at this. F of 2 pi will give us a negative 10. And we have sine of 2 pi minus 2 pi divided by 2. Of course, the 2's will absorb. So we have negative 10. Of course, this is a 0, so we have another negative. And let me make sure this is clear. So we have a negative pi. So this just gives us 10 pi. So these are the endpoints. Notice we have a 0 at 0, and we have this value, 10 pi, again, 3.14 times 10. So that gives us a rough approximation there. We'll often use 3 and 3.14 to do some crude approximations just when we need ballpark figures, okay? So one thing I also want to note is the following. Since we have this extension to the real line, we can see that the value 5x, or that particular part of the function, will take over. So we might have some more interesting detail closer to 0, but as we extend, we see that this takes over. And so as another aside, the limit as x approaches infinity of f of x, again, the 5x will dominate and we'll just get infinity. And then, of course, the limit as x approaches negative infinity of f of x, again, the 5x will dominate and we just get negative infinity. Of course, we're doing this because of the fact that the sine function is bounded between -1 and 1. And so it will not introduce any kind of effect at the extremes when you've got this term hanging out, okay? So again, another interesting aside by looking at the function extended to all real numbers. Now, let's check a few other numbers. Let's look at f of pi. So we get -10 sine of pi, again, that's another 0, minus pi over 2. So here we get what? -10 times negative pi over 2. Of course, the negatives absorb, and we just get 5 pi. 2 into 10 is 5. Okay, that's a positive number. So we're thinking maybe we've got another 0 that's not quite apparent to us. And now let's look at maybe something a little closer to the first quadrant, pi over 4. So we have -10, and we have sine of pi over 4 minus pi over 4 divided by 2. Now, sometimes when you factor things, it's easier to see magnitudes, and factorization is so important. I mean, it gives us clues that we just would otherwise miss. So we have -10, and of course, sine of pi over 4 is 1 over root 2. And of course, we can bring the 4 downstairs and get pi over 8. Now, when we look at this and we think, you know, how can we reduce this to a form so that we can compare these two? And we need a 1 here. So let's just do a little bit of smoke and mirrors. So -10, 1 over root 2, and multiply and divide by 1 over pi. So this will give us a 1, and then, of course, an 8 over pi. Now, if we compare the two denominators, and this is why I did this, 8 over pi, of course, pi is 3.14, so this is a number bigger than 2, but of course, the square root of 2 is smaller than 2. So this term will be larger than this just because of that fact that we observed. So this, in this case, this part is positive, but made negative, so this is less than 0. So what we're seeing here is that if we look at these two inputs, they give us different signs of the output. So this implies that there exists, and we'll see if there are more, there exists C between pi over 4 and pi, such that, in this case, f of C equals 0. So we get another 0 other than 0, and that's important. And of course, this 0 will be reflected through the origin. So we've got the C here, the additive inverse is also another 0 on to the left of 0 using the odd nature of the function. So that's really important. We just replicate the detail, but of course everything gets shifted below the axis or above, depending on where it exists, to the right of 0. So that's actually very interesting here and can help us with our sketch of the graph. So this is good. So nice information here. So we have this information, which is kind of like pre-cal, but with like a little intermediate value property that wasn't stated basically with continuity. So now, again, let's just kind of focus on this. So we've got some interesting information. We have the EVT. We have the existence of a 0 that lies between pi over 4 and pi. And we also have the fact that we have a guaranteed max and min closed bounded set. We have the utilization of the symmetry if we extend to all real numbers. So now what we want to do is say, okay, well, let's try some calculus. So f prime, again, we have the -10 factored, so that still stays to the outside, and we can easily differentiate inside. So the derivative of sine is cosine, and the derivative of the x over 2, that just gives us a -1/2. So the factorization made that real simple. And of course, it made this analysis very simple. So now, of course, we can say this equals 0 if and only if cosine of x equals 1/2. And so we can apply the inverse cosine function. So x equals the inverse cosine of 1/2. And of course, that's just pi over 3 using our unit circle. And then, of course, the second solution in 0 to 2 pi will just be subtracting this from 2 pi because cosine is an even function, right? So we have 2 pi minus pi over 3, which is 5 pi over 3. So we've got boundary values or critical numbers. I mean, when it comes right down to it, we're just looking for elements in the domain or not in the domain that can produce a sign change. That is, these are like markers in the domain that says, okay, the sign doesn't change here, or it does change. And that's actually extremely important when we're trying to analyze functions. So now we've got the existence of these two real numbers, we can do a sign analysis of the first derivative. So let's do our 0 and our 2 pi. And then we have the pi over 3 and the 5 pi over 3. So now, of course, we just go back to our derivative because that's going to be the linchpin of all of this. So we just put a little box around it to remind us what it is and where it is. So now what we can do is an extreme value. Notice that the 0 factor here exists to the first power. So it has a multiplicity 1 in its existence. And so sign will necessarily change at zeros. So, of course, at these two guys. So now what we can do is if we just pick like maybe a pi over 6 here, the cosine of pi over 6 certainly exceeds 1/2. So this factor is positive, but made negative by the negative in front of the 10. So we're below, then we have to cross and then cross. So here we have negative for decrease. So we'll do a downward arrow. And then we have increase because we have positive, increase, positive, and then down arrow for decrease. So this makes the analysis so simple that the work that we see that we do in calculus really requires good bookkeeping. That is, keeping track of signs and factorizing things in a way that lends to our understanding of sign and magnitude. Okay, so now we have what? We have what do we call it? The valley, We have decrease, increase, so we have a relative min. The relative min will be f of pi over 3. And now we have increase, decrease, so we have what we call a relative max, f of 5 pi over 3. Okay, so let's compute those, because these will certainly be important when we're trying to sketch a graph. Let me get hold of some paper here. Here we go. Now, what we want to do is notice that with these values, we're going to have more detail with the graph that was not available to us in our prerequisite courses. Okay, so let me go ahead and write down the original function. I'll cover this part up. So let me just write this down, and then we'll move to the new page. So we have f of x in our factorized form is -10 sine of x minus x divided by 2. Okay, so that gives us values there. And then, of course, what we want to do is do our relative min. Relative min is f of pi over 3. So this gives us -10 sine of pi over 3 minus pi over 3 divided by 2. So we have -10 and sine of pi over 3, that is what, √3 over 2 from the unit circle, minus pi over 6. Now, one thing we can do, we'll go ahead and clean this up and then write it in a way so we can estimate it. But first, I'll go ahead and factor the 6. So we have a -10 and a 6. So 2 into 6 is 3. So that gives us a 3. Excuse me. That's right, 3√3. And then, of course, minus the pi. Now I'm going to reduce this and show you a little trick. So this is what -5 divided by 3 if we divide both by 2. And now we can move the 3 back inside. You thinking, well, we could have done that before, but this is easily done this way. So we have -5. And we have the 3's absorbed, √3, minus pi over 3. So this sets up for a crude approximation, which is fine. That's all we need. So now we can say this will be approximately -5, and we can use like a 1.7 for the square root of 3. And then, of course, just treat the pi as roughly 3 or very close to it. So we can just treat that as a 1 for a crude approximation, which is all we need. We just need ballpark figures for our graph. And so this gives us what, a -5 times a 0.7. So that gives us a -3.5. Again, just a crude approximation, just to get a ballpark figure for our graph, because that's all we're doing when we sketch it. Now let's do the relative max and do the same technique. So we have f of 5 pi over 3, which will be -10. So we have sine of 5 pi over 3 minus, again, 5 pi over 3 divided by 2. So now we have a -10, but of course, we're in the fourth quadrant where the sign is negative, the reference number being pi over 3. So we get the -√3 over 2 in this particular case, -√3 over 2. And then, of course, we have minus 5 pi over 6. We'll do the same thing again. So we get -10 over 6, and we get the -3√3 minus 5 pi over 6. Now, oh yeah, excuse me, sorry, 5 pi. I'm looking back at the original. That's one nice thing about math. It tells you exactly what to do. So now do what we did before and do the negative 5 over 3, divide the negative 10 and the 6 by 2, and that gives us negative 3 root 3 minus 5 pi. And of course, you're thinking, got all these negatives, just get rid of them. They absorb anyway. So this will give us 5, 3. Let's go ahead and move the 3 in. And let's see, so we've got what, 5, and then we've got what, root 3 minus 5 pi, and I'll kind of put the 3 under the pi part. So notice here, the negatives absorb, and moving the 3 back in absorbs the 3 here, and of course the 5 pi over 3. Now we can just do our crude approximation. So 5 will have a 1.7, and now of course this will approximate with a 1. So that's just going to give us, in this case, so we've got, let's see, oh, now this is all plus, ding. So plus what? 5. So again, notice all of these absorb. I should have done that. That was not very clear. And so of course this is all plus. So this gives us 5 times 6.7. So that gives us a 5 and then a 3 with the 30, what, 33.5. So again, a crude approximation. It's a little on the high side, but that's okay. All we need is just an approximation to make a sketch. And so when you're looking at relative sizes of minima and maxima, you just need a rough approximation. So what I'm trying to show you here is a way to approximate without just developing a bunch of decimals that aren't really going to help you when you're trying to sketch a graph. This approximation is more than efficient, and it allows you to utilize your understanding of the unit circle. And of course, it checks your arithmetic as you do it, which you could easily see. So now we've got, again, the relative max. So let me just kind of write by this here, relative max occurring again at 5 pi over 3. And then we have the relative min occurring at pi over 3. So the analysis here is kind of the most we've done. We're pulling out all the stops, so to speak. So then we're thinking, what's the last part of the puzzle, the shape of the curve? So let's go back to a real simple version. Notice we want f double prime. So let me write down what we'll use. We'll just take the derivative here of this one. So we've got what, negative 10. And the only thing that's left is the cosine, so that the derivative of cosine is negative sine. And then, of course, the minus 1/2, of course, is just a 0. So that was simple. When we factor, we get real simple. So now, of course, the negatives absorb, and we get 10 sine x. So the nice thing about the fact that we have the algebraic with the transcendental is that as we differentiate, the derivative formulas don't get more complicated. Sometimes they do. They actually simplify. Now, of course, very simple. This equals 0 if and only if, well, this is one of our friends. X is just, as I've said many times when I've been doing this analysis, just an integer multiple of pi. Okay, well, we don't need the endpoints. I mean, we're good with that, but we can certainly look for interior. So now we can just say when n equals 0, just go ahead and write it down. We get x equals 0. When n equals 1, we have x equals pi. And of course, all of these are here. One's on the endpoint. We don't really care about that, but we have this on the interior. And then, of course, n equal to 2, we just have x equal 2 pi, which, of course, is in the closed set, again, the endpoints. So these would actually mark changes in the concavity. So again, that's important. If you want to extend the graph, you certainly can do that. But whatever you get to the right of 0, you automatically have to the left by the odd symmetry. So now notice, if we're just confining ourselves to the closed bounded set, you want to start extending things, it gets more interesting, clearly. So we have the pi here. So again, the negatives have absorbed. So now, of course, in the upper arc of the unit circle, the sine function is positive. And of course, we have multiplicity 1 of the sine factor. So here we have plus, which is concave upward, and we have minus, which is concave downward. So that was easy. So now concave upward, open set 0 to 2 pi, and we have concave downward, open set, overkill, 0 to pi, and then, of course, pi to 2 pi. So again, the math is irrefutable. It tells us exactly what we need to know. We don't always want to believe it, but it reminds us. And so now, of course, we have a point of continuity here. So we have a point of inflection, point of inflection. So this will just give us 0, comma, well, I just love the 0 and the 2 pi, but I want to leave the pi out. Pi, f of pi. And so now we can go back here. Again, look at the definition. So let me just remind you, well, it's up here. We've got this right here, so we'll just fill it in with that. So we have, and I did pi, well, actually back on the first page, it's just 5 pi. I've already done that, so we got it. So this gives us, just go back to the previous work, we get pi, comma, 5 pi. So this was a previous calculation. So previous calculation. So I don't have to start over. Previous calculation. So the complete analysis of functions is a time-consuming process, but the individual pieces you can do. But again, you need to have the analytical technique to work through the algebra and the arithmetic. That's the key to doing calculus, because it's just pluses and minuses and some fractions. That's all we ever do, it seems. And well, that's exactly what we do. That's the what we call it, sophisticated arithmetic. So now let's put all of this together. So we're just looking at the interval here, 0 to 2 pi. So we can go ahead and plot the extreme values and the endpoints. And now what I want to do is make sure we have all of the other items. So the important items would be, of course, I'll stretch this out so we can see it. So we have the 0, we have the 2 pi, and of course, right in the middle, just kind of eyeball that, we have the pi. And then we've got the critical numbers from our critical point analysis here, the pi over 3 and the 5 pi over 3. So let's see here, about right, pi over 3, 5 pi over 3. And now we can spread this out a little bit. We've got our crude estimates. So let's go back over here at pi over 3, we have roughly negative 3.5. And then, of course, the overestimate here, 33.5 for the relative max at 5 pi over 3. So we'll mark this out. So we've got like about, let's just say a negative 5. And then we'll do, let's make that just a little bit smaller because we don't have, didn't write this down as much. So we'll just say we've got like about a negative 5. So we'll do 5, 10, 15, 20, 25, 30, and then 35. So we'll mark it off that way to get a little space. So 25, 15, 5. And so we've got our negative 3.5 at pi over 3. So say about crude approximation about right here. And let's see, 5 pi, so roughly a little over 15. The point of inflection about right here. And then, of course, we have the 5 pi over 3, 33.5. That's the over, but we'll survive. So about right here. And then we come down a little bit at, let's see, what do we have? We had 10 pi. So yeah, so let's see, what else did we, what was the 2 pi, or did I actually do that one? Let me check to see if I actually did that one. Oh, I didn't, and I'll do that one. So but I thought I had checked all the endpoint. Oh, here we do. Yes, we got it. Right there. Right there, 10 pi, right there. So we'll say like about 31.4. So we'll come down a little bit about right here. Okay. So we've got all those values. And of course, at 0, we've got 0. That means leave out 0. And notice here with the concavity, we're concave up 0 to pi. And then from pi to 2 pi, we're concave down. So we can, again, keep nice and smooth. Nice and smooth. And then, of course, we've got our 0 here that we know existed from the intermediate value theorem. And then we switch concavity to downward. Here to pick up the max. And then back down a little bit. There we go. Okay. Now that is a work of art. No, the analysis is a work of art. My picture is C minus. Okay. But the idea here is this was not available to us before. So we've got what? We have f of x equals negative 10 sine x plus 5x. So x element 0 to 2 pi. So what I'm saying here is that when you do the complete analysis, we have EVT, and notice here we didn't have endpoint extrema. They were all localized. We have a elegant point of inflection, but again, this curve, again, if we wanted, you can just reproduce over here through the origin and get this side of the graph for free. Okay, using the fact that the function extended to all real numbers or to any symmetric set relative to 0 is odd. So you can just do this here and then just replicate this part over here. So you can get for free half the graph. So again, let me just summarize what we've done. We started with the basics. We showed that if we extend to all real numbers, we have an odd function that has some very simple end behavior. We analyzed, and now, of course, we know between pi over 4 and pi, we have a 0, and there's the C right there. This is the C from the intermediate value theorem right there. That's the C that we computed from the intermediate value theorem, which we saw right here. Okay? So that analysis, and another thing too, if we notice, with this, we're increasing. So as we move from pi over 3 to 5 pi over 3, we start to increase. And so there's no way to double back. So we only had one zero. The first derivative tells us that this zero here, at least, is unique. We have this, but we don't double back any time in this interval. And clearly we don't do that here. So the intermediate value theorem was important in that it verified that we had a zero here, at least one, and we've proven that we just had one in that particular interval. And now, of course, relative min and relative max using the first derivative test, increasing, decreasing, can't beat it, can't beat it. You know, the beauty here is decrease, increase, decrease. Right here, can't miss it. And then we go ahead and do some crude approximations, even though they're more than sufficient, some approximations of our relative extrema, just using basic arithmetic techniques, and then using the second derivative to evaluate concavity. And then, of course, we get a point of inflection that occurs at the ordered pair pi, 5 pi. So when I say this is a work of art, this is a work of art because of the calculus analysis and the pre-calculus analysis. Combining the two gives us this marvelous analytical technique to provide a beautiful structure. And you don't have to plot 500 points. Now the idea here is that the analytical part of this is what is important. As you work with functions in more math classes and you work with functions in physics and engineering and all your STEM courses, the analytical technique is so important. So we got a lot of output from that analysis. And use this as you work on other problems that probably won't be as difficult. So now what I want to do is cover a more straightforward example. That is, this next example I want to show you, I went ahead and worked it out, and it's a little bit simpler than the last one, but I just wanted to show you the analysis so you could compare this to the work that you did in pre-cal in college algebra. And I wanted to do like kind of a line-by-line analysis of what you would do in the prerequisite course and how you pretty much made it work. We saw with the last problem that the calculus was really the driving force. But when you analyze polynomials and rational functions, you do have a lot of benefit from the pre-calculus techniques, especially with the sign charting that gives you either plus infinity or minus infinity with vertical asymptotes. And so the analysis is usually not as difficult, but it certainly can be tedious when you actually think about derivatives, as you see in the lecture notes. But what I wanted to show you is this particular function, that is y equals the negative of x cubed minus 3x plus 4, and we have the domain extended to all real numbers. So in this problem, I don't think they explicitly say what the domain is, so there's no need to restrict it. Now, what I've written here is analyze using calculus and the standard techniques. Now, what I did was kind of transform us back to the pre-calculus techniques. That is, the first thing you would do is probably factor the negative, because when you work with bound theorems and things like that, Bound's theorem, excuse me, you always want a leading coefficient that's positive for the sign conventions to work. So when we do that, we notice we have a very simple rational zero, which is 1. I mean, of course, you have 4 minus 4 and you're done. So the first thing you would do is run to the synthetic table and divide by x minus 1. So of course, we put in our coefficients 1, 0, 3, and -4. Of course, we always need a placeholder for powers of x that don't exist. Bring the 1 down. 1 times 1 is 1, plus 0 is 1, and then 1 times 1 is 1, plus 3 is 4, and then 4 times 1 plus equals 4. Add that to -4, get a 0. So we factorize. That is, now we have y is equal to the negative of x minus 1 from the factor theorem times the reduced polynomial, which is x squared plus x plus 4. Again, just standard fare for pre-calculus techniques. And so now, of course, we know this has no positive zeros, but we're thinking probably no negatives either. The AC method doesn't work, but we check the discriminant and we have b squared minus 4ac. So that's 1 squared minus 4 times 1 times 4. Of course, that's a negative number. And then we have zeros are imaginary. Okay, so again, the good thing about doing the analysis with the quadratic equation is that when we don't have real zeros, that's a good thing to know. Then the sign is fixed for that factor. So the next thing you would do in the pre-calculus is say, okay, we have one boundary value. It has multiplicity 1. And so you'd mark your 1, and then you'd say, okay, well, if I take an extreme value like 100, we just have positive, positive. And then, of course, the negative throws this into the negative category. And so, of course, with multiplicity 1, we'll change sign at 1. So to the left of 1, we have positive, which means the graph is above the x-axis. And to the right of 1, we have negative sign, which means the graph is below the x-axis. Now, of course, since there's only one boundary value, again, we have the limits at infinity. We understand the arithmetic of the limits at infinity from our last lecture. But of course, this gives you the end behavior for free. So now, of course, since this doesn't define any horizontal asymptotes, as x approaches infinity, clearly we take the sign here of negative, we get negative infinity. And then, of course, as x approaches negative infinity, y takes the value here, which is positive, so we get infinity. So that's just a freebie. So you're thinking just from that, you can sketch a graph. I mean, considering the last problem, it would have been pretty difficult I mean, we could have maybe tried a little bit, just check some points and then, draw, but there would be nothing about that graph that would make us feel good because we needed the analysis of the derivative. Here, because we've got the function becoming infinite and negatively infinite as end behavior, and we've only got one real zero, there's only so much detail. And we're thinking we could kind of cheat a little on the detail, knowing that we've looked at a lot of pictures of polynomial graphs generated by computers. So we're thinking, maybe we can get by with that. So now what I wanted to show you is how we can use a little bit of pre-calculus with calculus, and the calculus making the process a little bit easier. So if we take the original function here, ladies and gentlemen, and differentiate, the negative is already there, but we get what? 3x squared plus 3, of course, the -4 giving us a 0. And now we can factor, and we get -3 times x squared plus 1. Now, of course, the factor x squared plus 1 only has imaginary zeros. This is always positive. And then, of course, with the -3 gives us a negative derivative. And it's always negative, okay? It's always negative. That's really important. So now, by increasing, decreasing, we see y decreases on the real number line. And when we would have drawn our graph, we would have started, above the x-axis and then just kind of drooped down, pick up the intercept, the x-intercept, and just keep going. And of course, pick up the y-intercept, which I haven't mentioned here, which is 4, we pick up those and we're thinking all we can do is decrease. So at least that was something that we thought was relatively assured. I mean, we had no reason to believe that it would be more complicated than that. Okay, well, this is starting to show that, again, decreasing throughout the domain, which is all real numbers. Now, what does that give you when you have this kind of situation occurring? Now, you can also have situations where you have isolated zeros and the sign of the derivative does not change. That can produce the same effect. So what we have here, if you compare this to f of x equal x cubed, you see that the derivative is always positive. I guess you do have a zero at 0, but the sign doesn't change. So when we look at the first derivative test, it's like, well, the sign doesn't change at 0, so we don't have a relative extremum. This is even one step above that. This is never 0. But again, I'm just letting you know that that won't impact the conclusion I'm about to make. So now y is definitely 1-to-1. And why do we know that? Well, we can actually use Rawls' theorem. Because remember, with Rawls' theorem, you have to have 2 points, f of A, f of B, that have the same output. And then if you have the continuity on the closed set and the differentiability on the open set, you have the existence of at least one horizontal tangent. Okay, so if we made that assumption for this function, then this would have to say that the derivative would necessarily be 0 at a point intermediate between the 2 zeros that we're saying exist for the function. Well, there's no way it can be that way. So the idea is that if you're saying that a function is not 1-to-1, you use the fact that the derivative is never 0 to counter that. So the Rawls theorem is a very popular way of proving the 1-to-1-ness of functions that have 0 or have derivatives that don't change sign. So that is a very elegant way to get the 1-to-1-ness without a whole lot of work. Again, think of that Rawls theorem. We use that to prove the mean value theorem. It's a very, very useful result. Now, I just notated here the way that I teach my pre-calculus students to show that something is 1-to-1. Now, of course, this can be difficult algebraically, but it does give you some option that avoids the use of the derivative when you don't have it in your vocabulary. So what we do is we kind of start out the same way we did here. We just assume that f has values in the range that are accommodated by different inputs. Okay, so when we start out that way, if we think the function is 1-to-1, our goal is to show that it was the case that A does equal B, and that's why they were equal in the first place. So what we do is we just take the original function here and we evaluated A and evaluated B. Now, algebraically, it starts out pretty simple. The 4's absorb, and then we can multiply through by -1 to get rid of all the negatives. Now we can simply transpose everything to one side and get a cubed minus b cubed plus 3a minus 3b, and then factorize. Okay, of course, this is the difference of 2 cubes. That's our bread and butter from college algebra. That gives us a minus b times a squared plus ab plus b squared. And then, of course, we can factor the 3 from the a and the b. Now, of course, we can factor the a minus b from both, and we get a squared plus ab plus b squared plus 3. Now, this particular quadratic, we say quadratic in A, again, is never 0. It has only imaginary zeros. So if you treat this as quadratic in A, the discriminant now, of course, will just be, in this particular case, b squared, which is really a b squared minus 4 times 1 times the constant term b squared plus 3, which is clearly negative. So this has no real zeros. So the thing is that by zero product, the only thing that's left is that A minus B equals 0. So that implies that A must equal B. So again, this gives you the one-to-oneness without the use of the calculus. Again, when you think about a particular function as being one-to-one, you just set equal. You affirm the existence of two values of the function being the same that possibly have different inputs. Okay, so when we're trying to refute this one-to-oneness by Rolle's theorem, we get the contradiction. So that actually is a very nice, slick way to do it. But once you do it, you don't do it again. I mean, you don't do this again. I mean, you've got this derivative that never changes sign. You're done. You've got the one-to-oneness. But when you're looking at a specific function, you've got to go through this algebra every time. That's not a given. Okay, so the use of the derivative is a true marvel of the calculus, and we will find uses of this later in this course, and you will find uses of this in subsequent calculus courses. So it's an extremely, extremely useful tool. Now, that's it. So all we have left is just the derivative, and of course the graph is what you thought it would be. So when we take the derivative, we just go back to the simplest version of it, which is right here. So the -3 is factored, and we just have the derivative of x squared, which is 2x, and the derivative of 1, which is 0. So we just have this simple derivative, and boy, don't we wish they were all that simple. And of course, now this is clearly 0 and x is 0. So now we're thinking, okay, well, we take an extreme value like 100, and of course this sign gives us negative, and of course the 0, 0 occurs to multiplicity 1, so the sign must change at 0. So to the right of the 0, we get negative or downward concavity, and to the left of 0, we get positive or upward concavity. Now, of course, y of 0 is just the y-intercept, which I didn't mention before, but now we've actually distinguished it as a point of inflection. So the point of inflection is actually the y-intercept. So ladies and gentlemen, that's all we need. That's all the information we need. We thought we had something that looked like this before we did the calculus, but now we have a kind of slender function. Notice it's decreasing throughout its domain, but it's drawn in such a way that there are clearly no horizontal tangents. And notice here we have the point of inflection. We go from, in this case, upward concavity to downward concavity. Now, when you drew your polynomials in your prerequisite classes, you most likely drew them like this. Or if you had more zeros, you'd have peaks and valleys, which again was something that was easy to intuit. So the graphs that we had back in the prerequisite courses were actually very good, but they did lack a certain precision that we have from the analysis of the derivatives. So I want you to compare this to the last example where the calculus was actually quite important to get a degree of precision. Here, since this function is invertible, the graph is a little bit simpler. And so again, remind yourself, y inverse exists. And so again, you could use the techniques of reflection in the line y equal x. But again, what we're going to find, as we did with implicit differentiation, is that we can compute values of the inverse function using the original function, and that's going to be very interesting. So again, if you're already thinking about it, if 0, 4 is on y, then 4 zeros on the inverse. So we'd have something, again, and I didn't draw this very well, so we have like 1, 2, 3, 4, because I've got scales that are a little bit different there. So that's kind of bad. So we have 4, 0. And then if we have 1, 0, we have 0, 1 here. So when you look at this, you're thinking, okay, we can do, again, let me just kind of do this. We have our line y equal x. That's our symmetry line. And so now you can think of just kind of running this way, you know, to mimic this piece. And then you can notice here that as we look at this piece, notice this would have to kind of reflect over this way. So let's see if we can actually draw this. So let's see here. So now, let's see. So we've got to pick up this point here, and we've got to get really close to the axis. So let me go ahead and extend this. So we can do, again, just kind of get really close to this. So I'll just say, let me just kind of move like this. Nice and close, about like that. And then we have to come across and pick this up. Like that. So this would be y inverse. Again, using the symmetry, again, this part here coming this way, picking up this point, and then moving that way. So we get a nice symmetry there. So again, not a work of art, but again, using the pre-calculus techniques, we can draw a picture of the inverse, and we knew how to do that in college algebra. So again, what we're seeing now is that we have the marriage of the pre-calculus techniques with the calculus techniques, and we get the full picture. And notice, we can't explicitly solve for the inverse function, but we can still exploit the differentiation process. Okay, so I hope this has been illuminating. I think what you're going to find as you continue to work on these problems is that your analysis will get better and better. Don't assume that you leave anything behind, ladies and gentlemen. Everything you do is important. We use all of the strategies that we learned in our prerequisite courses. We can't do without them. But then we add the structure of the derivative, the concavity. We add the structure of the increasing, decreasing. But again, the symmetry line is just like the change of base formula for logarithms. That's not going anywhere. That's all good stuff. So as you continue to practice this, notice that it is bringing together all of the ideas that we've been working on for the last two chapters. So I hope this is a good time for you to kind of assimilate everything and feel at least more confident about the arithmetic of calculus. We'll see you later.